this talk is based on this published paper in Physical Review B, which was supervised by Professor Chen. And well, the title is basically related to how we can test modified gravity theories by using quasi-normal modes and or black hole perturbations, which are very interesting because it is related to the recent development of gravitational wave astronomy. So why modified gravity? We know that Einstein gravity is very good to describe a huge portion of our universe, but it still has some problem because, for example, in a very high energy scale, we have UV incompletion of the theory, we have singularities like black hole singularity, Big Bang, or even daytime singularities, and so on. So it is believed that we should have some kind of quantum gravity, which is a concrete description of our universe. But so far, we don't know how this theory should be constructed. We have no idea yet. So effectively, we may consider some kinds of modified gravity theories in such a way that we correct the original Einstein-Hilbert action a little bit or somehow, such that the new theory can resolve the original problems in Einstein gravity. And in the low curvature limits, these theories have a nice behavior. It reduces to generativity. That's our expectation. But you can imagine that in such a way, we may have several amounts of these modified gravity. So the problem is that how do we test them and how do we even falsify these theories? So one of the examples is by using the gravitational waves. You know, recently we have direct detection of gravitational wave from LIGOs, Virgo collaborations. So we may test these theories via, for example, the speed of gravitational wave, which according to the recent detection of neutron star merger, that the speed of this gravitational wave is very close to the speed of light. And we can also test this theory with the polarization of gravity waves. And here I want to discuss another possibility which is very related to the merger event itself, which this is the so-called ring-down signals of gravity waves. So ring-down signal corresponds to the post-merger stage of an event, and it can be described by black hole perturbation theory, and it is characterized by the quasi-normal modes. I will explain here. So this is the schematic plot of this gravitational wave signal that we have during a merger event. So initially, imagine you have a binary system of black holes. They rotate around each other, but their orbit, their radius, their distance become smaller and smaller because they lose their energy by emitting gravitational waves. And in the end, they merge together to form the final black holes. But imagine just after the merger, the distortion of this system is so huge. But in the end, this distortion should gradually relieve to its final configuration, the final black hole. So the final stage of these signals correspond to the oscillating, but the amplitudes of the gravitational wave should gradually decrease. So this corresponds to some kinds of complex frequency oscillations in which the real part corresponds to the oscillation and the imaginary part of the frequency corresponds to the decay of the amplitudes. And the reason we call these ring-down signals, and it is described by the so-called quasi-normal modes. We know what normal mode is. It describes the natural oscillation of the system. And the name quasi means that this system is actually a dissipative system. It loses its energy. So the amplitude of this normal mode is decreasing. So that's why it is called quasi-normal modes. And in general relativity, actually, these quasi-normal frequencies, the frequency of these oscillations, are just characterized by the quantities of black hole. For example, the mass, the charge, and the speed, if the black hole is rotating. But in other gravity theories, if the theories contain other parameters like here alpha and beta, then this frequency should also depend on these parameters as well. So that's why we may use these frequencies in modified gravity to see how this frequency deviates from its GR counterparts and to test these theories. So in this paper, we consider two kinds of gravity theories. The first one is the FO gravity coupled with nonlinear Born-in-field, nonlinear electromagnetic fields. And we use the Platini variational principle in such a way that the theory is varied with the metric, physical metric, and then affine connection independently. And then we have a second order equation of motion. And if we include a charge here, it can be expected that if the charge is very small, then the solution of black hole, charged black hole in this theory reduces to the usual Reisner-Nordstrom black hole in general relativity. But if the charge is large or if the radius is very close to the event horizon, even close to the singularity, we have a totally different solutions from general relativity. And another interesting thing is that if we have this function f of r equal to r, which is just the original Einstein-Hilbert action, then we have the Einstein-Born-in-field black hole, which has been widely discussed in the literature before. And another model that we are going to consider is the so-called Eddington-inspired Born-in-field gravity. So as you can see here, the gravitational action is corrected, is modified by this Born-in-field or square root structure. So you can see that there's a curvature here and there's a square root. So in principle, this model was originally proposed in order to remove the divergence of the curvature, because we put this curvature inside this square root. So in principle, this curvature has some upper bound. So we want to remove the original singularity in general relativity by using this kind of modification. And actually, this kind of structure was originally proposed by Dyson and Gibbons in 1998, but they proposed this theory under metric variational principle. And the theory has, the equation of motion has higher order derivative and it has ghost. It is problematic. So we also formulate this theory in the Platini variational principle, and again, this theory has a nice property in the sense that it recovers GR when the curvature is small. But the charged black hole will deviate from Reisner-Nordstrom 1 inside the black hole, for example. So here I just show you the metric function. The black curve corresponds to the Reisner-Nordstrom black hole in general relativity. And the blue, red, and green are just the metric functions of these black holes in different models. So you can see outside the event horizon, in which this curve is larger than 0, is positive. They are very closer to each other, but inside, once they're inside the event horizon, then you can see a huge deviations from the Reisner-Nordstrom solution. So we want to consider these models, these solutions, and we calculate their quasi-normal frequency to see how this frequency deviates from Reisner-Nordstrom 1. So in order to do that, there are a lot of ways. I will briefly introduce it. So in this paper, we consider the quasi-normal modes from massless scalar field perturbations. So imagine that you have a black hole and we throw a massless scalar field around this black hole, and we treat it as a test field of test perturbations. So this field is described by the Klein equation because we follow the geodesics. And if we after some decomposition of the field or some redefinition of fields, this Klein equation can be written in this Schrödinger-like form with a special potential here. And we just draw a potential like this. So this point corresponds to the event horizon, and this peak, well, this is just a peak of potential. And I should say that in order to derive the quasi-normal modes, we can treat these equations as a scattering problem in like quantum mechanics, because it is very similar to Schrödinger equation. So after imposing some proper boundary conditions, we can solve the eigenvalues of these equations, and we can derive they correspond to the quasi-normal modes. So you can imagine that the peak, the properties of this peak of the potential is very important. It carries almost all the information of these quasi-normal modes. So the peak is very important in calculating the frequency. And here I just want to show you the results. So the upper figure corresponds to the real part of the frequency. As I said, again, in the cosine normal mode, we have also the imaginary part correspond to the decay of the amplitude. And we consider the ratio between the frequencies with that of the Reisner-Nordstrom black hole. So as you can see, when we turn off the deviation, for example, the charge or the Bohr field corrections in the model, the frequency reduces to that of the Reisner-Nordstrom black hole. So it means that we have a good agreement with the GR counterpart. But when we increase the corrections, then you can see that there are several kinds of different deviations in different models. And so because this model is constructed in the spherically symmetric background, so in principle the equation depends on the multipole number which is used in the spherical harmonics we have L here. And we see that even we choose another value of this multiple number, the qualitative behavior of these results are still the same. Another interesting issue is that if we consider the Eikonel limit in which the multiple number gets to infinity, which is a very large value, then the potential can be approximated in this way. And the interesting part is that the peak, as I said, the peak of the potential is very important. And the peak of this approximated potential is just the photon sphere of the black hole. It's just the null circular orbit. So it means that the results of frequency can be solely described by the photon sphere. So the real part corresponds to the rotation period frequency, and the lambda, the imaginary part corresponds to the Lyapunov exponent, which quantifies the instability of the black hole, of the photon sphere. So this is the behavior of the Eikonel limit. So you can see the tendency is still the same. And here we also choose another kind of example. We consider R plus alpha R squared, and we can see that when we turn off the value of the Bohr field correction, the solution reduces to Reisner-Nordstrom black hole. It has a good agreement with GR counterpart. So let me go to the conclusion. So here we show that a complex cosine normal frequency can be used to test theory because they contain the information from the parameters in the theory itself. And here we consider two kinds of gravity theories, the charge black hole in these two theories, and we show how this frequency deviates from their GR counterpart, and it has its graded limit. And also the cosine normal mode in the Eikonel limit can be described by properties of the photon sphere. And basically these properties is very important in cosine normal mode. Sometimes it is violated, but at least in this case, it is also satisfied. And as I said, here we just consider the massless scalar perturbation. But actually, if we want to study gravitational wave, we need to consider the gravitational perturbations itself. We need to perturb the gravitational equation like Einstein equation itself, and we can construct the corresponding potential. And because of the limitation of time, I will not be able to describe our current results on the gravitational perturbation in these theories, which was also published in the beginning of this year. So yeah, so that's it. Thank you.
So next year you're going to have another.
I don't know.
Okay. Any questions? Yeah.
What's the source of dissipation?
What is the source? Oh, I think it depends on the natural properties of this system. So it is described by the boundary conditions of the model. So actually, in this system, the boundary condition of this wave, we have an outgoing wave moving away from the black hole. So I think this part of the wave function, this part of the perturbation carry away the energy of the system, and that's why we have that's why this system is losing energy because of the boundary condition.
questions? Maybe I ask a question. You said that the inside horizon different theory give quite a distinct different result.
Yes.
Can that be tested? Because it's inside event horizon.
Right. So the tricky part is here.
Yeah.
So the potential here, you can see that actually what really changed the quasi-normal is the potential itself. And the potential, we only consider the potential outside the event horizon.
Oh.
Yes. So
that means you cannot test the prediction inside the event horizon.
not exactly. So you can see in this figure, even though we only consider the exterior side of the black hole, the metric function has a small deviation from their GR counterparts. So you can see that, okay, for example, the position of the event horizon is changed. So this also changed the shape of the potential. That's why we can have a different spectrum. We can have a different quasi-normal frequencies.
So it can be tested.
You can, in principle, yes, but the deviation is not that huge.
Any other questions?